So now let's look at the next topic, a focused ion beam. So first, we compare electron and ion beam. For the electron, we know they are very small, and they can penetrate into the atom and kick out inner shell electrons. For the ions, it is very big, and it cannot kick out inner shell electrons. As a result, it will not generate X-ray. The electron is small, has high penetration depth, a low mass, high speed, and negatively charged, and will use magnetic lens. For the ions, it is big, the penetration depth will be small, and if it stays in the material, it will become dopant. And also because it has very high mass, has slow speed, but very high momentum. When we have a high momentum, we can do the milling. So this is the main application of the ion beam compared to the electron beam. So for the electron beam, the only thing we can do is to expose the resist, to modify the property of the electron beam resist. But for the ion beam, we can not only modify the property of the polymer resist, but also we can remove the material by milling or sputtering process. Ions is positively charged, and we use electrostatic lens. So we will see those things later on. So this table also compares the property of the electron and ion beam. So first we know that for the mass, so the gallium, so we use gallium ion. So we use gallium ion. So the gallium ion has atomic number of 31. So 31 atomic weight will be about twice 62, about 62 kilogram per mole. So this is like the atomic weight, roughly. So the atomic weight is roughly double the atomic number. We know each of the neutron or proton, the mass of the neutron or proton is 1,800 times that of the electron. As a result, for the gallium ion, the mass is 130,000 times that of the electron. So because we have the high mass, so we have the high momentum. So this is most important for the ion milling process. For the momentum, we know the energy is given by 1/2 mv squared. So the momentum is equal to a square root 2 me. So higher the mass, higher the momentum. You can see the momentum here is about more than a few hundred times that of the momentum for the electron. So here the beam size is always about, it can go to the nanometer range. For the penetration depth, for the ion beam, we go to a few tens of nanometers. The typical is about 1 nanometer per kilovolt. But for the electron beam, it can go to more than 10 micrometer for the polymer or 2 micrometer for the case of the iron or silicon when we use 30 keV. So we can use both electron beam and ion beam for imaging purpose. For the imaging purpose, we care about the yield of the secondary electrons. For the case of 100, so 100 ions can produce 100 to 200 secondary electrons compared to 50 to 70 for the electron beam. So as a result, so the ion image for the same beam current, the ion image will be stronger than the electron image. There will be no backscattered electrons for the case of ion beam, but it can sputter away 500 atoms on average. So this is called a sputtering yield. The sputter yield. The sputter yield is how many atoms kicked out per incident ions. This is called the sputter yield. So we can generate 30 secondary ions. For the electrons, it can generate X-ray, but no X-ray for the case of the ions. So now let's look at the ion source and ion optics. So we look to generate electrons. But to generate electrons, there are two ways. So one is the heat. So we can heat up. Another way is the electrical field. So we can either use high temperature or we can use high electrical field to generate electrons. For the case of ions, so we can also use high electrical field, but we cannot use heat. Because if we heat up the material, the material will be vaporized. So what you get is the atom, neutral atom, rather than ions. So there are 4 types of the ion source. The first one is called electron bombardment ion source. So the idea is very simple. So you have the electron here, bombard a gas molecule, for example, or argon molecule here. But when the electron collects with the argon molecule, the argon will be ionized to create the argon ion. So this is done in a chamber. So it's done in a chamber. You have the chamber, you have the argon gas, you fill it with the argon gas, and you have the filament. You have the hot filament, you apply a voltage, hot filament, this filament will emit electrons. So this is a case called electron bombardment ion source. So this one is used for the mass spectroscopy, mass spectrometry. So what mass spectrometry uses the ions? If you remember, one of them is called SIMS. It's called SIMS. So this is the secondary ion mass spectroscopy. The secondary ion mass spectroscopy. The next one is the gas discharge ion source. The gas discharge we know is nothing but it's plasma. So gas discharge is the same thing as. So this is the plasma ion source. So we'll talk about plasma ion source later on. The third one is called the field ionization source. Field ionization source. So in that case, so we need a very high electrical field. So first you have a sharp tip that generates very high electrical field. Then you fill the chamber with some gas molecules, for example, helium. So when the helium comes to the close to the tip surface, because of the very high field, so the helium will be ionized. So when they ionize, it will be accelerated, and you get the helium ion. Sorry, it's not hydrogen. It is the helium ion. You get the helium ion. So this is called the field ionization source. So the last one is the liquid metal ion source. It seems the idea is the same. We also need a very high field. But in this case, so here we have the gas molecule in the chamber that got ionized. But for the liquid metal ion source, the type of material itself, so the material itself come out. Sorry. So the material itself come out. It got vapor, got ionized, then it come out. But this is the liquid metal ion source. So for the case of focused ion beam, so the most popular one is the gallium. So this gallium is produced by the liquid metal ion source. So we'll talk about this one first. So you have a emitter here. This usually made of tungsten. It's tungsten emitter. The material is the tungsten. So you have the liquid metal. So here is the liquid metal here. In this case, it's gallium. So the metal will wet the surface. So it goes to the surface, moves to the tip part. So we have very high field, 10 to the power 8 volts per centimeter. Then it gets ionized, then gets extracted. Extracted by this extractor, we have ion come out. Ion come out. So what happened? It was found that normally the field here, extractor, the voltage here needs to be at least 22 kV in order to extract ion. This angle here is about 30 degrees, and emission along different directions is rather uniform. The uniform emission along different directions. So the voltage, the energy spread, so delta E. Is about 15 electron volts. So this is a big number. So we know that. So for the case of electron, for the case of the cold field emission, for the case of cold field emission, if we remember, the delta E is about 0.3 electron volt. So you can see that this for the cold field emission source, the energy spread is only 0.3 electron volt. And so the total energy like 30 kilo electron volt. Energy spread is only 0.3. But here we get 15 electron volt. So what will be the effects of this very large energy spread? As we know earlier, so we have the aberrations. So one of the aberrations is called a chromatic aberration, which is proportional to this one. A chromatic aberration. This one is proportional to delta E. As a result, it is more difficult to focus ion beam because of this chromatic aberration. So this is the electron microscope image of the tungsten tip. This is the tungsten wire. But you can see it's not sharp. So it is nothing sharp. So we know we want a very high field, but here it's not sharp. If it is not sharp, then the field will be low. Because the field is given by something like this. So this is the electrical field, right? This is the electrical field. So Q is the charge. Q is the charge on the surface. When you apply a voltage, there will be a lot of charges. Then we have R at the lower part. So when they are bland, the R is big, so the field is not high. But what happened? So we have the liquid. So in this case, you have gold germanium liquid, gold germanium alloy. This one is alloy, gold germanium alloy. So we have a liquid. We apply very high field, it will be really sharp. So this one is called a Tyler cone. It's called a Tyler cone. It is very sharp. At this sharp point, the electrical field will be very high. Then the gold or germanium, it will be ionized and come out. So here I ask you one question. Will Tyler cone form if the field direction is reversed? If the field goes to the downward, if the field goes this way, so will there still be the Tyler cone? Yes, there will be Tyler cone. As long in the liquid, as long as you have the electrical field, the liquid will be stretched. The liquid will be stretched. So you will also form the Tyler cone. But you will not have the gold or germanium ions. So what you will have? We have the field along this direction. So what will come out? So this is the case of the electron source. This is the cold field emission or short circuit emission. This is the electron source. Because the field point downward, you get the electron emitted. Now here is the photo of the liquid metal iron source. Liquid metal iron source. So here is the idea of the current come out. You have the molten gallium and you have the tungsten. So now I want to ask you, so do we really need liquid metal? Do we really need liquid metal to have the iron source? Can we use solid metal? For example, if we do not have this, if we don't have this molten gallium, this tungsten, we have a very sharp tungsten tip. So this is the tungsten, no gallium. Will there be emission or not? So will there be like tungsten ion come out? So there will be. But the problem is what is the difference? So if we have the pure metal, it's very difficult to make it sharp. But we have this Tyler cone is really sharp. So we have the pure metal, you need a higher voltage to emit the ion, because otherwise the field will not be very high. But for the case of the liquid metal, because the field at this sharp point is really high, so you need a lower voltage. So the conclusion, so it can be liquid or solid, there will be field emission, there will be emission of the ions, but the amount of the field, amount of the potential applied to the tip will be different. So the field will be the same, but potential will be different, because we have the liquid metal, easier to make it sharp. We have the solid, it's more difficult to make it sharp. So when we pick tungsten, so when we pick a gallium, so first it melts at 30 degrees, very low temperature, so very easy to get the liquid. It has low vapor pressure, so it's good for the high vacuum, and the amount of the doubly charged of the ions is almost negligible. It's 10 minus power 4. It's almost very, very small. The lifetime, 1500 hours, is good enough. Atomic number equals 31. So the momentum, we have high enough ions, heavy enough ions. The momentum is high enough, so it is efficient to spot away the material from the sample. So we know that to focus the electron beam, so we use the magnetic lens. We use magnetic lens to focus electron beam, because if we use electrostatic lens, so we have a very high field. We can have very, very, very high field. So we have very high field. There is the chance of the arc, right? There may be some arc, discharge. So we have the arc discharge on the electrode. Then electrode may got burned. As a result, we use magnetic lens to focus electron beam. But magnetic lens is not good to focus ion beam, so because of those formulas. For the electrostatic force is given by this formula. So as long as it's the same for the electron ion, they have the same charge, so the force is the same. But for the magnetic field, the force is given by this Lorentz force. So this speed of the particle is given by square root of 2qv. Q is the charge, v is the acceleration voltage divided by the mass. And because of ions, the mass is very big, so the speed is very small. When we have very small speed, you need really, really big magnetic field to have the same force. But we know it's not easy to generate very high magnetic field. As a result, we use electrostatic lens to focus electrons, even though it is not as good as the magnetic lens in the focusing property. But we cannot have so big magnetic field, so we have no choice. So when we have very low current, a few picoampere, this is very low current, we can focus the ion beam to about 5 nanometer. So when we get a larger current, like 60 picoampere, alpha equals 1 milliradians. So 1 milliradians is given is how many degree? So 1 milliradians is 60, roughly 60 divided by 1,000 degree. Right? This is my 1 milliradians. So it's smaller than 0.1 degree. Now we have this chromatic aberration because we know for the ions this delta E value is, we just talked about, go to 15 electron volts is too high. So this delta E value is too high. So we have very large energy spread, we get a chromatic aberration. So when we have even larger current, we get spherical aberrations. This one is the proportional to alpha cubic. So obviously, the larger current means bigger angle. So bigger angle, this one will go up very quickly. As a result, this spherical aberration will be more significant than chromatic aberration when we have large current. So here is the current and the beam size. You can see the higher the current, the bigger the beam. So this makes sense. This is the probe diameter in nanometer. Higher the current, the bigger the beam. So you can see, for example, when we get 1 nanoampere, the beam size become how big? You see, comes to here. It's maybe 50 nanometer. 50, it's very big. This is only 1 nanoampere. So we have higher current. If we get 100 nanoampere, the beam size will be micrometer scale. It's really big. On the contrary, for the electron beam, so we can have less than 10 nanometer beam size even at 1 nanoampere. And we can use, when we use 100 nanoampere, for the case of electron, the beam size will be about 50 nanometer. So you can see it's much smaller. That is the main reason that even for today, so people use electron beam lithography much more than focused ion beam lithography. Because for the focused ion beam, you cannot have high current. But for electron beam, we can have very high current. This will give you faster exposure time. Another reason is, so electron beam is much cheaper than focused ion beam. For the SEM, for the scanning electron microscope, the cost is about $500,000. But for the focused ion beam, it will be more than $1 million. So this is the beam. So this is the beam profile. So this is the beam diameter. So this shape is Gaussian beam. So what matters when you want to make very deep structures? The beam tails, they will be important. So you have the beam even beyond the beam diameter. So those tails will make a significant amount of the material. Will make a narrow trench or narrow holes. So here we talk about liquid metal ion source. The next one is the plasma ion source. The plasma ion source. This one corresponds to this one. Gas discharge ion source. So the idea is very simple. So you have the chamber. You have the gas molecule. Like it can be argon, or it can be xenon. You have the gas. Then you have this RF antenna, this coil. This coil. So we have the coil, you have the induction. So this is called ICP. It's called inductively coupled plasma. So we have the coil, it is inductor. So this is inductively coupled plasma. So we have the plasma, there will be a lot of ions. Then the ions will be extracted from here. So this is extractor. So the diameter here is 200 micrometer. So 200 micrometer. So this 200 micrometer looks like not a small number, but the virtual beam size is not that big. So the virtual beam size is about 10 micrometer. So this is the virtual beam size. So we will see. So now we can, if you don't remember, I will show you again. You see here, so even though it looks like the beam is very big, this is very big, but actually the virtual size, this is the real size. This one, this is the real size, it's very small. This one is the virtual source. The virtual source is also very small. So that's what I said previously. So even though here is 200 micrometer, so the actual virtual beam size is about 10 micrometer. So it's not small, but it is okay. So here is the beam current. So this is the beam current and the beam size. So this curve, this white curve here is the same as this blue curve. So what do you see here? So we want higher current. You can see the beam size D50. D50 is the beam diameter. Half beam diameter goes up really quickly. It's given by D50 is proportional to a current power 1.5. Where does this 1.5 factor takes? This 1.5 is given by is 3/2. So this 3/2. Now let's look at the previous slide to see how this 1.5 come. So the spherical aberration given by alpha cubic is proportional to alpha cubic. So the beam current IB is proportional to the alpha square. Because the beam current is proportional to this, you put the aperture on the left and on the right. So the smaller the aperture, the smaller the alpha angle, you get smaller current. It's proportional to the alpha square. That's why you get this formula here. So this is D50 I upon power 1.5 is equal to alpha 3 times. Because the current is proportional to the alpha square. So you can see we need a very high beam current. Then this is the liquid metal iron source. The white line is not as good as this solid line. But this black color solid line corresponds to the casing of the 30 kV xenon plasma source. You can see that's smaller beam size for the larger beam current. So nowadays we use xenon rather than argon. So normally when we do the sputtering, we use argon. But for the casing of the plasma iron source, so we use xenon. There are a few reasons. So first, the xenon has higher atomic number. So this one, the xenon has higher atomic number. So the heavier mass, so the sputter yield will be higher. The momentum will be higher than argon. The sputter yield will be higher. Secondly, the delta E, energy spread for the casing of xenon is smaller than for the casing of argon. This is the second reason. The third reason, the xenon is easier to ionize than argon. So you have more ions if this is xenon than if this is argon, because xenon is easier to ionize than argon. So here is the comparison of the different iron sources. So we will look at the gas field ionization later on. So we have talked about liquid metal iron source. We talk about the gallium. Another choice is the silicon and the gold. So what do we use? We use the silicon and gold alloy. We use a silicon and gold alloy. They always come together. So why we need silicon and gold alloy? Because we know that to melt silicon we need 15 degrees. So melt silicon. To melt gold, we also need about 7 degrees. But we have the alloy. So we have the gold silicon alloy, which 18% silicon. Then the melting point is only 260 degrees. That's why we use gold and silicon alloy. Gold silicon alloy as the source, so that they can be melted at this pretty low temperature. But one problem, so both gold ion and silicon ion, they will come out. So both gold ion and the silicon ion, they will come out. So then we need to know which one we need to pick one. We need to pick one of the ions, not both of them. But this is realized by this filter. So this is called this filter is called it's called a Wien filter. It's called a Wien filter. This is the schematic of this Wien filter to pick up either gold ion or silicon ion, but not both. So what do? You apply the electrical field this direction, you apply magnetic field the other direction. So when the charged particle moves downward, for the casing of electron beam, the Lorentz force will be this one. This one will point to the left. The electrostatic force will point to the right. So those two forces, they will cancel out. As a result, when the electron beam come in, it will go forward. But actually here we don't use electron, so we have the ion. So we have the ion. So the ion is the idea is similar. So when the two forces is equal, with opposite direction, it will go through directly. But this one, so this is the condition. So when the speed is given by E over B, then it will go straight. Otherwise, it will be deflected. So when it goes straight, it goes through this aperture, to get selected. The next one is the plasma source. The plasma source, as we said, the main advantage for the plasma source is it can get very high current. For the low current, it's not as good as gallium, but for the high current, it gets smaller beam size. But nowadays, you can get even to microampere current. So as a result, you can mill really big areas, big volume. You can mill up to 100 micrometer cubic. So you can mill the volume 100 micrometer cubic of the silicon within a few hours. This is a pretty big area for the case of ion beam. Now let's look at ion-solid interaction. So when the ion hits a target, when the ion hits a material, it will generate a lot of secondary electrons. This will be useful for the imaging purpose. Some of the ions will be boxed back. This is called backscattered ions. It can also generate some items from the substrate. Some ions get inside the material, become implanted ions. So this is how the signal is generated with the ion beam. So we know that for the case of electron beam, there are more signals for the case of electron beam. For example, when we have electron beam coming in, so we have the backscattering electrons, and we have the accrete, and we also have the photon. If the material is semiconductor material, if electron comes in, it can create electron hole pairs that generate photon, accrete, and BSE. But those signals will not be generated. We have the ion coming in. So here is the trajectory done by the Monte Carlo simulation. It's called Monte Carlo simulation. So basically, you assume you have like a 10,000 ion coming in. Then you follow the trajectory of each of the ions. So you can see for the case of the 50 electron volt ion energy will go to about 50 nanometer. So 100 electron volt, 100 kilo electron volt, you get about 100 nanometer. This is 100 nanometer. So roughly you get 1 nanometer per kilo electron volt. So you should know this number. So it's about 1 nanometer. So we have 1 nanometer per kilo electron volt. This is much smaller than the case of electron beam, because we know electron beam, it can go to a few micrometers at the 30 keV. But at the 30 keV, for the gallium ion beam, it just goes to like about 30 nanometer. 30 keV goes to 30 nanometer. So we have the gallium ion bombard the surface, and it will cause a lot of damage. It can become ion implantation. So when the amount is very high, it can form a second phase of gallium. You have the gallium phase inside the host material. And to make the surface amorphous, it will create many defects, weaknesses, interstitials, dislocation, and also heating. So the number of the defects created is given by this formula. It is about E over ED. So this E, the first E is the ion energy. So this first E is ion energy, like a 30 kilo electron volt. The second ED is the displacement energy. For example, for the case of the silicon, this silicon. So to kick this silicon out, you need to break many electrical bonds. You need to break many of the chemical bonds. So this one, you break 4 of the chemical bonds in order to kick this silicon out. This will be more than 10 electron volt. So the ED is 10 to 20 electron volt. As a result, you can see this is a kilo electron volt, 30 kilo electron volt. This 10 to 20 electron volt. So there will be on average 1,000 defects per ion. You can see a lot of defects will be created. We have the ion beam. So here we have the factor of K 0.8 and also factor of 2. So you don't need to worry about the K or 2. You just need to know is roughly on the order of E over ED. That is good enough. So the gallium is the acceptor for semiconductor materials. Because the gallium, we know it is in the same group as the boron. So boron, this is the periodic table. So gallium is the same group as the boron. As a result, it is the acceptor, like a boron. So here you can see this is the damage by the indium phosphide. This is a 3,5 semiconducting materials. So this is a 3,5 group 3 and group 5 semiconductor materials. So you can see for the case of the 40 keV, so for the case of the, I think this should be 30 keV, you have about 40 nanometer amorphous. So the top layer here is amorphous. Here is the single crystal. But typically, as you can see, for the case of silicon, 10 keV, 6 nanometer, 30 keV, 28 nanometer. And we have talked about earlier, roughly it is about 1 nanometer per 1 nanometer per kilo electron volt. So this roughly like this. So we have 30 kilo electron volt. It will penetrate about 28, 30 nanometer. So how to minimize the damage? So one thing you can do is that you start with the high energy, so high energy like 30 keV. So when you have high energy, the milling will be fast. You get higher current, you get faster milling. Then near the end, you use lower keV or even lower keV. When you use 2 keV, only the top nanometer become amorphous or gets damaged. But in reality, it's not so easy to realize low keV. When we have low keV, the liquid metal ion source will no longer work very well. So usually we use more than 10 keV, not, for the machine we have, we don't go to 2 keV. So thanks very much.